This question builds on the prior question that we had where we were trying to calculate the stress in the cables from this object hanging from two of these cables. And we used previously the idea that the sigma was equal to the force over the area. Now we're introducing that sigma through Hooke's law is equal to E times epsilon. We can rewrite our epsilon and we get that sigma over E will give us the strain. So the question that's being asked here is, what is the axial strain in the cables? Well, in the previous question, we calculated the stress and we realized that to get the strain, we just have to divide by the elastic modulus. So from question 4, we have this expression for the sigma, and we have now the ability to just divide the sigma by E to get an epsilon, or axial strain. The epsilon then ends up being this large thing. So if we go back to Google, and I think I still have it open, all right, we have this equation that we need to divide by the elastic modulus. Now, the answer is not going to be in megapascal, so we can get rid of that. And we already did division by that, but that's okay. We can just add another division and put 207 gigapascals in there. Let's take a look at the numbers though. The numbers might have changed, so now we have 0.5 times 1,000 kilograms per meter cubed. The height is going to be 1.2, or the thickness is it's 1.2 meters. So this is actually a typo that I made. Whoops. Okay, so that's, let me get the pen out. Okay, so this is actually 1.2 meters, not 1.2 centimeters. And we have a width of 1 meter. We have a thickness of 1 centimeter. So let's change those. So this is going to be 1 meter. This is going to be 1 centimeter. Okay, that stays the same, 9.8 meters per second squared. And we have an area of 0.2 centimeters squared, like that. Okay, we hit enter. What do we get? All right, okay, so we get something that's dimensionless, so that's important. That's an indicator that we're probably on the right track. And if we look at our values, we have something times 10 to minus 5. Well, it's asking for the result in microstrain. So do this conversion, I don't think it will tell us exactly. I can't say in microstrain, I don't think. Well, let's see what happens. Nope, it doesn't like that. That's not something that's familiar with. But what I can do is I know that there are 1 million microstrain in a strain, or I guess, without dimensions, just unitless. So what I'm going to do is multiply by 1e to the 6, and this will give us the answer in microstrain. So the answer is 16.6 microstrain. How do we do this in Google Colab? Well, I'm going to pull up the previous code that we had, and I'm going to go ahead and try to save another copy. All right, I'm going to duplicate this, so creating a copy, so I don't lose my previous thing. And I'm going to say that this is, I guess, session 5, question 6. No, that's not right. Section 5. This one's actually 5. Okay, the other one was 4. Well, anyway, I will just say 5.2, just for keeping things straight. And all I needed to do here is divide by the elastic modulus. Okay, so I don't have to rewrite all this code. I can put these numbers in that are appropriate. So the height is 1.2 meters. The width was 1 meter now. This thickness is still 1 centimeter. Gravity is the same. The cross-sectional area was 0.2. Okay, and now I need an elastic modulus. So the elastic modulus is 207. All right, but that's going to be E9, so I get gigapascals. And my sigma is this. So I'll just say that I want an epsilon, and that's going to be sigma divided by E. And I'm going to print instead. Actually, I'll leave this. I'll just copy it because you know what? It's not bad. I know that my sigma is going to change a little bit, all right, because I have different parameters. So we'll do a separate line just to calculate the epsilon. And we have epsilon. Okay. Now remember, the stress that was calculated out was in units of pascals, so that's fine. And it would, and this 1 e to the minus 6 only applies to when I was printing it out in megapascals. So I don't really need to change that value. It's sigma is sigma divided by so oops, that's a typo, pascals, right? Like that. It's going to give me a unitless number. But if I want it in microstrain, I don't multiply by 1 e to the minus 6. I multiply by 1 e6. And now I can write microstrain like that. Okay. Hit Control Enter. And it's getting upset because, of course, I forgot again to load the library. Now I load the library. I think it's got that part done. Now I try to run this again. And what do I see? We see that we get a different value of stress and we get 14.2 microstrain. That's a little bit different than the 16.6 microstrain. So where did we go wrong? What did I do incorrectly? Well, I come back up here and I look and I see, oh, that should have been 1.2 meters, not 1.4 meters. Okay, 1, 1, 1, da, 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 da. Okay, now I hit enter and I get 14.2. Okay, so we see that these techniques do show agreement for the numerical calculations. I hope you watched the whole video because if you had stopped before we did the Python, well, that wouldn't have been the right answer. But you probably had different values to plug in, and maybe you caught my mistake prior. Thank you very much for watching. I hope this information is useful.